Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
So, hello and welcome to today's webinar in the AI for Good program. Today's presenter, Fiona Lippert, is a postdoctoral researcher in the Space Research Organization of the Netherlands. She is trained as a computer scientist at University of Tübingen and University of Amsterdam in the Netherlands, and has worked in many application domains of AI, ranging from medical imaging to criminology, atmospheric remote sensing, which is her current application focus, and also ecology. And in this application domain is her current talk, which is provides insights into her PhD research done at the University of Amsterdam, in which she developed process-guided AI pipelines for forecasting bird migration. So we look forward to your talk, Fiona. The floor is yours, and look forward also to a discussion afterwards.
Thank you so much for the introduction. Let me share my slides. All right. So today I will share some of the work that I've done during my PhD at the University of Amsterdam, as Alexander just mentioned, where I worked on forecasting and better understanding bird migration using process-guided deep learning. And so bird migration is really this incredibly fascinating natural phenomenon with billions of birds flying across the globe every spring and fall to move between their breeding and wintering grounds, which often lie thousands of kilometers apart. And in this talk, I'm specifically focusing on the migrations of small songbirds, like you can see here in the pictures, that often migrate during the night and in extremely large numbers, leading to these massive and highly synchronized redistributions of biomass across entire continents. And through these large-scale movements, these migratory birds effectively couple otherwise completely disconnected ecosystems. They transport nutrients between them, disperse seeds over very large distances, and interact with local communities and food webs along the way. And that way, these migrants really play an important role for the functioning of many ecosystems along their migration route, and they contribute to biodiversity worldwide. But unfortunately, the world that these birds are flying through is changing rapidly. So now large parts of their migration routes are dominated by urban areas, agriculture, all kinds of human infrastructure, which all leads to more and more conflicts arising during these migrations. For example, it's estimated that in the US alone, around 230,000 birds die every year from collisions with wind turbines, and around 600 million birds die every year from collisions with buildings, especially due to light pollution that compromises the navigation of nocturnal migrants at night. And so ideally, we would like to be able to mitigate these collisions and other human-wildlife conflicts to protect migratory bird populations and the ecosystems that they provide. But to do this effectively, we essentially need to know when and where birds are migrating, ideally a few days in advance so that stakeholders have time to prepare appropriate mitigation measures, for example, to initiate temporary shutdowns of wind turbines or to coordinate large-scale light-out campaigns for urban areas. And so one way to gather data on these otherwise really difficult to observe migratory movements is by using operational weather radars. Because these radars have been originally designed to monitor precipitation, but they can actually also detect if there are a large number of birds in the air, and we can make use of that. So how this works is that weather radars emit pulses of energy at different directions and elevation angles, and they then measure the amount of energy that is reflected back to the radar by either raindrops or, in this case, birds. And we can then translate this measured reflectivity at different times and locations into estimates of bird densities. Now, in addition, weather radars can also make use of the Doppler effect to measure radial velocities that provide information about how fast birds are flying towards or away from the radar station, which then provides partial information about the underlying movement patterns. We can then aggregate many of these high-resolution measurements within a small area around the radar to translate these relatively noisy and incomplete measurements into more reliable estimates of average bird densities and average velocities in the vicinity of the radar. And now the exciting part is that these weather radars are typically organized into large networks, like the NextRad network in the United States that you can see here in this animation. And that means that we can combine the information from all these radars to get a very comprehensive picture of migration flows over large geographical areas, which would otherwise not be possible. And so in the remainder of this talk, I would like to discuss, on the one hand, how we can use this data to develop forecast models that predict migration flows at the continental scale. And then in the second part, I will explore how we can interpret these forecast models ecologically to learn something new about the underlying bird behaviors. So let's get started with the forecasting problem. And before going into any details, let me highlight a few key challenges that we are facing when developing migration forecast models based on weather radar data. So first of all, radars provide only partial information on the migration process. You can already see this here from this animation, where there are large unobserved areas in between radar stations where we never really observe what's happening in the air. And in addition, weather radars also cannot provide information on what is happening on the ground or close to the ground. Now, the second key challenge is related to the fact that radars really only measure population level quantities. And we, for example, don't know what the underlying species composition or the distribution of ages and sexes is, which all influence migration behaviors and strategies. And lastly, our understanding of migration strategies, responses to environmental conditions, and how these may vary depending on the spatial and temporal context is still rather limited. And that means that we don't really have reliable, purely process-based models available that we could use to generate accurate bird migration forecasts in the same way as traditional weather forecasts are generated, for example. So to overcome these challenges, current state-of-the-art migration forecasts build on relatively simple local regression models that link the migration intensities measured at a particular time and location to the corresponding local environmental conditions, including, for example, time of the day, time of the year, certain landscape characteristics, and all kinds of weather variables like temperature, wind, and precipitation. And after training, such a model can then easily be applied to data from operational weather forecasts to generate corresponding migration forecasts for arbitrary locations of interest. And here on the right, you can actually see the latest migration forecasts for today, actually, generated by the Verstcast team in the United States, and the corresponding lights out alerts that they issue based on this forecast on the bottom. And I really encourage you to check out their website and explore how these migration patterns in the US change over time and space. Now, the downside of these local regression models is that they cannot really explicitly capture the spatial and temporal dependencies that are inherent to the movement process that we're trying to predict. And that means that the predictive power of these models is rather limited because they, for example, cannot leverage information about past and current bird densities at one location to predict movements at a downstream location along the migration flyway a few hours or days later. And in addition, these models are also limited in the ecological insights they can provide because they're not rooted in any kind of mechanistic process description, but they're purely built on local correlations. So let's talk about how we can overcome these limitations of current migration forecasts by instead taking a process-guided deep learning approach, where we explicitly encode the spatial and temporal dependencies of the migration process into a data-driven forecast model. And so here our process knowledge comes in the form of a very intuitive description of how bird densities in the air change during the migration process. And we can conveniently express this in terms of the continuity equation that you can see here. And so this equation describes essentially the temporal evolution of bird densities across the spatial domain in terms of two main components. On the one hand, we have a local source sinc term here on the right, representing birds taking off from the ground and therefore causing bird densities in the air to increase. Or birds land at the end of the migration night and therefore decrease bird densities in the air. And then the second component is the spatial term representing bird movements in the air. We can then discretize this equation in time and space to obtain a mechanistic movement model that we can in principle use to simulate migration flows. And for example, we can do this across a hexagonal grid covering our entire radar network in the United States, as you can see here on the left. And so now in this discretized version, the spatial movements are essentially expressed in terms of numerical fluxes between neighboring cells, while the takeoff and landing are modeled for each cell independently. And they capture essentially the fluxes between the ground and the airspace represented by that cell. Now, to use this framework for actual prediction, we of course need to know what these fluxes actually are and how they vary as a function of various environmental conditions. And that's where the deep learning part comes in, because as I mentioned earlier, we don't really know what exactly birds or how exactly birds decide when to take off and land, how fast they fly and in which direction they fly. And that's why we use neural networks, and specifically here in LSTM, to parameterize these two flux terms in our equation as a function of environmental conditions and current bird densities. And the combination of this mechanistic movement model with a data-driven parameterization of these fluxes then results in a hybrid model architecture that we call flux RGNN, which is essentially a recurrent graph neural network, where the graph represents the neighborhood structure of our grid cells, and the messages along the edges of this graph neural network correspond exactly to the spatial fluxes in our mechanistic movement model. So there's this really interesting duality between the numerical movement model and the implementation in form of a GNN. And that means that we can use standard deep learning software packages like PyTorch to implement this relatively easily, while still being able to interpret the different model components ecologically. And so before diving into the results, when we apply this in practice, I want to spend some time discussing how exactly we parameterize these fluxes to ensure that they remain ecologically meaningful. Because if we were to directly predict these two flux terms with the LSTM, we might run into issues where bird densities suddenly become negative because more birds are predicted to leave a cell than are currently in that cell. And so ideally, we want to avoid this and make the model as physically consistent as possible. So let's have a look at how we parameterize the spatial fluxes between neighboring cells. So the goal here is to ensure that the number of birds remains a conserved quantity, meaning that the flux from cell I to cell J needs to be equal to the negative flux from cell J to cell I, so in the opposite direction. And we achieve this by not predicting these spatial fluxes directly, but by instead predicting bird velocities in each cell, and then using a finite volume method scheme to compute the corresponding numerical fluxes, which by design of the finite volume method will ensure local mass conservation, or in this case, bird conservation. Similarly, for the source sink term, representing takeoff and landing within a cell, we again want to make sure that not more birds are predicted to land than are currently in the air in that cell. And we achieve this by separating the takeoff, so the positive contribution, from the landing, so the negative contribution, and parameterizing the landing part as a fraction of the current bird density, which is predicted by our LSTM together with the takeoff component that in this case cannot be constrained any further because we don't explicitly model birds on the ground. So we simply enforce this to be a positive number. All right, so finally, let's talk briefly about how we can train this hybrid model then, based on our weather radar data. So the first thing that we need to talk about is how to actually compute prediction errors for both bird densities and velocities, because our model predicts quantities at the cell level, but our observations are tied to the sparse locations of the radar network. So we need to establish some kind of mapping from cell level predictions to a kind of synthetic radar level observations that we can then compare to our actual radar measurements. And for that, we introduce a relatively simple observation model that essentially computes a weighted average across cells that overlap with the measurement area of a radar station. Now, the second aspect that I would like to discuss here is how to combine the bird density and velocity loss functions in a way that both encourage accurate predictions of migration intensities and at the same time ensure that our predicted fluxes remain ecologically meaningful. Because what can happen in the extreme case where we don't put any weight on velocity errors is that we run into equifinality issues. That means that there are multiple different parameterizations of the model that can generate the same output in terms of bird densities alone. So you can imagine a scenario where all changes in bird densities are attributed to the local source sink terms and completely neglecting the spatial component of the model. And that's, of course, not what we want, because that's not kind of a realistic scenario. Now, to avoid this, we need to carefully determine a good value for this lambda scaling factor that we apply to the velocity loss function, so that the model correctly disentangles the local takeoff and landing from the spatial movement. While still focusing enough on bird density errors to ensure that we in the end also accurately forecast migration intensities. So now let's have a look at the results and focus on evaluating exactly this trade-off between forecast accuracy and interpretability. So here I plot the histograms of predicted velocities in blue and measured velocities in red, separating it into the flight speed on the top and the flight direction on the bottom, and each for the three different values of this lambda scaling factor. And you can see that we run into exactly that issue that I just discussed, where for lambda equals 0, so where we don't use any velocity information, the model is able to infer the general migration direction towards the south in this case from bird measurements alone. but the corresponding speeds are severely underestimated. And that in turn means that the takeoff and landing will be overestimated because they compensate for the lack of movements and therefore changes in bird densities in the air. But as we increase this weight on velocity errors, the predicted speeds start to match our radar measurements more and more closely. And so that means if we can now show that, for example, for this lambda equals 0.1 case, for which the match seems to be quite reasonable, the corresponding bird densities are also predicted accurately, then we can be fairly certain that the corresponding source sink terms can also be interpreted ecologically in terms of takeoff and landing, even though we cannot directly measure or evaluate them. So let's have a look at the bird density evaluation. Here I show the results for a spatial cross-validation, where we train the model on a subset of radars and then evaluate the predictions for independent years, both at the radar locations used during training and the held out ones to evaluate really how well we can extrapolate to unseen locations. And we then compare the root mean square error of predicted bird densities of our flux RGNN model to an XGBoost model, which is essentially one of these local regression models that I discussed earlier. And you can clearly see here that our process-guided forecast model achieves much lower errors than this local regression model. And it's also more robust when extrapolating to unseen sites. So this is really good news. And when we look at the effect of the velocity regularization on our bird density predictions, we do see that larger lambda values lead to slightly increased bird density errors. But this is really quite marginal, especially compared to the much larger errors of this local regression model. So from this, we can basically conclude that we are able to now generate accurate spatiotemporal migration forecasts that can also be interpreted ecologically in terms of takeoff and landing within each cell and the aerial movements between neighboring cells. And this really provides a lot of additional information that we could not get with more simple local regression models. And I also included an example forecast here for 3 consecutive nights with considerable migration, where you can really nicely see this progression of nocturnal mass migrations, where I would argue our model really shines because it can leverage these spatial and temporal dependencies that result from this migration wave moving through the country. All right, so now that we've discussed and evaluated our process-guided migration forecast model, I would like to move to the second part of the talk, where I will explore how we can interpret this model and the learned relationships to better understand the underlying migration behaviors. So let's jump right to in this. And here I want to focus specifically on trying to better understand how takeoff decisions are affected by local weather conditions. And so in this plot here, you can see the nightly takeoffs predicted by our model across the entire United States for 9 different spring migration seasons in these blue lines. And in general, you can see a very clear seasonal pattern with takeoffs increasing in early spring, peaking around May, and declining again towards the beginning of June. But so you can also see a very strong interannual variability, especially around the peak migration period. And that's really typical for these nocturnal mass migrations, where most nights really show relatively low activity. And there are just a few nights throughout the entire season where there are these extremely intense migration peaks. And typically the timing of these peaks is largely determined by the corresponding weather conditions, such as by favorable winds, mild temperatures, but also things like air pressure, humidity, and precipitation. Now, so these main drivers are relatively well known, but what is still quite unclear is how exactly birds respond to these different weather conditions and especially how this may depend on the particular spatial and temporal context. So that's what I would like to focus on here. And so specifically, we're trying to answer these questions by using techniques from explainable AI to systematically analyze the relationships learned by our process-guided forecast model that we now here train on all available radar data to really provide the best possible estimates of these unobserved takeoffs across time and space. Now, so one important challenge that we need to address here is the fact that weather variables generally correlate with migration patterns for two main reasons. On the one hand, we have the general climatology, for example, the seasonal and diurnal patterns of temperature at a specific location, which correlate very strongly with the general seasonal phenology of migration intensities. On the other hand, we have more transient weather phenomena that lead to short-term responses of birds. For example, you can think of birds avoiding flying during heavy rain or stormy conditions. And in these individual responses then in turn lead to short-term deviations in takeoffs from the phenological baseline. And that exactly corresponds to this interannual variability that we set out to better understand. So the question is how we can disentangle these short-term weather effects from the more long-term phenological trends to avoid any confounding due to correlations with the general climatology. And we achieve this here using what we call contrastive explanations, where the main idea is to focus our interpretations on takeoff anomalies instead of absolute takeoffs. That means that we compare the actual prediction to a reference prediction that is generated by replacing all weather variables by their corresponding average value for each location and time of the year, which then essentially represents conditions that can be expected by birds under normal conditions in this spatial and temporal context. And the resulting reference predictions then essentially capture the general spatial, seasonal, and diurnal migration trends. And the corresponding takeoff anomalies should then capture only these short-term effects of weather on the takeoff decisions of birds on the ground. And so to analyze the specific effects of each weather variable, we then attribute these takeoff anomalies to the different weather variables by computing Shapley values. And so Shapley values are a method that originally comes from game theory, but is now commonly used as a tool in explainable AI. And it's designed exactly for these kind of applications where a difference in outcomes needs to be fairly attributed to different variables, while accounting also for all possible interactions between these variables. And so in standard explainable AI settings, Shapley values are usually used to explain why a model output deviates from the overall expected value of outputs. But so in our case, this approach would not be able to account for phenological trends that vary across space and throughout the season. And so that's why we slightly adapt the standard approach here to instead use this local reference value for each specific location and time of the year. But so all the nice properties of Shapley values still hold for our approach too. For example, that they are additive and that the Shapley values of all feature values of all the features that go into the model sum exactly up to this difference between the actual and the reference prediction. So here are our takeoff anomalies. Oops. All right, so now let's have a look at the results. And I'll start by showing the overall importance of the different weather variables in terms of their mean absolute Shapley value. And so what you can see here is that clearly wind is the main driver of takeoff anomalies in both spring and fall, which is what we would expect from what we know from the literature and previous studies on nocturnal bird migration. Now, what is also interesting to note is that temperature, for example, is really much more important in spring than it is in fall, while for humidity, it's the other way around. So we can already see from these overall importance values that there are very clear differences between the two migration seasons. So it will be even more interesting to dive into how this varies across different contexts. But so for now, let's just zoom in a little bit further and look at the actual effects that these variables have on the predicted takeoffs. And I'll here focus specifically on wind because it's the main driver in both migration seasons. And the plot here on the left shows the Shapley values of wind as a function of the actual wind conditions that go into the model predictions, so not our reference values. And specifically, I show the tailwind component here, which is the component of the wind vector that aligns with the main migration direction at a particular location. That means that negative tailwinds mean that birds experience opposing winds, while positive tailwinds mean that they experience supportive winds. And you can see that there's this clear sigmoid shape where in both seasons opposing winds lead to negative Shapley values. That means to decrease takeoffs. And on the other hand, supportive winds either lead to positive Shapley values, so to an increase in takeoffs in fall, or they have seemingly no effect in spring. And so this difference between spring and fall for the supporting winds is probably related to the fact that in the US, supportive winds are much more rare in fall than in spring. That means that in spring, favorable conditions are effectively the standard. So we can expect that most migrants will take off and resume migration whenever they are ready in terms of resting time and restoring their energy reserves. And they will only decide to stay on the ground if wind conditions or other conditions are unexpectedly unfavorable. And in fall, on the other hand, it's much more critical for birds to take advantage of these rare moments with supportive conditions to save energy. Okay, so sorry, I'm skipping again. Yes. Let's have a look at how these effects vary between different spatial and temporal contexts. In particular here, I show how the prevailing local wind conditions modulate how the actual wind conditions affect the predicted takeoff anomalies. So, for example, the lower right quadrants in these plots correspond to moments with unexpected opposing winds in regions with normally prevailing tailwinds. And as you would expect, these situations typically lead to a strong decrease in takeoffs compared to the phenological baseline. And similarly, the upper left quadrants then corresponds to moments with unexpected supportive winds in regions with prevailing headwinds, where we see a strong increase in takeoffs in fall. But even in spring, where we did not see any positive effects of supportive winds before, we can now see a clear enhancement of takeoffs in regions where supportive winds are rare. We can also see that in regions with generally opposing winds, birds appear to be less selective because even slight headwinds can lead to an increase in takeoffs. So it seems like in these regions, the relative improvement over prevailing wind conditions is much more relevant than the absolute tailwind in determining the effect on takeoff anomalies. And then we can do the same for wind conditions in the previous night, where now the x-axis for the two plots on the right correspond to tailwinds 24 hours prior to the prediction of our model. And we generally see very similar overall patterns as with the prevailing local wind conditions. namely that especially in fall, even slight headwinds can lead to an increase in takeoffs if the conditions improved relative to the previous night. And we again see that in spring, supportive winds can actually have a positive effect after nights with unfavorable conditions. So in summary, we can conclude that the effects of wind differ a lot between the two migration seasons, but they are also clearly modulated by both prevailing and past wind conditions. And that in turn indicates that migratory birds really dynamically adjust their behaviors and decision-making to the particular spatial and temporal context. All right, so now we've seen how we can build accurate and interpretable migration forecast models by incorporating prior knowledge about the movement process into a spatial-temporal deep learning architecture. And in the second part, we've seen how we can start generating new hypotheses about the underlying bird behaviors by carefully analyzing the learned relationships of our process-guided machine learning model. And so before I wrap up, I would like to take a step back and reflect a bit on the value of process-guided deep learning more in general. So imagine you're interested in predicting the behavior of some kind of complex dynamical system, like bird migration or any other Earth system process. And depending on the particular system you're interested in, you will find yourself somewhere on this plane where you will have a certain amount of prior knowledge about the underlying process on the y-axis, and you'll have a certain amount of data available on the x-axis. And so if you understand your system perfectly and you have a very accurate process-based model at hand, you can probably just use numerical simulations to make predictions about your system behavior, like it's done, for example, for traditional weather prediction. And if you then also have some observations, you can integrate them into your simulations using data assimilation techniques. Now, on the other hand, if you have really massive amounts of data available, nowadays you can probably also just use a fully data-driven black box deep learning approach, and it will work perfectly fine. And I would argue that, for example, with weather prediction, we are now really in the sweet spot where it's possible to generate very accurate forecasts using either traditional simulation or black box deep learning. But in many other cases, like with bird migration and many other biological or ecological processes, we find ourselves in this blank space where we neither have accurate process-based models available, nor enough data to really train large-scale deep learning models. And I think that's really where process-guided deep learning shines, because it allows us to reduce the data requirements and encourage consistency with available domain knowledge or theories, even if this domain knowledge might also be incomplete. And so there are, in general, really many ways to integrate available process knowledge with deep learning. But generally, I would argue there are two main approaches. On the one hand, you can explicitly constrain the solution space of a deep learning model, for example, by using a process-based backbone and using neural networks to learn parameterizations or correction terms, resulting in some kind of semi-parametric hybrid models like our flux RGNN model. And you can also design your neural network architecture based on more structural domain knowledge, for example, encoding causal graphs in the form of graph neural networks or probabilistic graphical models. And we've seen in the first part of this talk that these two approaches can actually sometimes be seen as two sides of the same coin, because there are many parallels between, for example, numerical discretization and the structure of common deep learning architectures like RNNs and GNNs. So a lot of these hybrid models can actually just be implemented as some kind of standard neural network architecture where you can interpret the different components, in our case, ecologically. Process knowledge can also be incorporated more implicitly to guide the learning process towards solutions that are consistent with prior knowledge, for example, physical constraints like mass conservation. And one way to do this is by formulating your process knowledge as soft constraints that are added to the loss function for regularization. But you can also think of other ways to guide the learning process, for example, by generating synthetic data with an approximate process model, and use this for pre-training your model or for some kind of data augmentation. All right. So throughout this talk, we've seen how this integration between process knowledge and deep learning can help us make more accurate and robust predictions. But it also opens up opportunities to improve our understanding of the model processes, especially for these hybrid models where we can explicitly attribute meaning to the different components of the model. And ideally, these insights can then feed back into further improving and refining our process representations, which eventually can lead to new generations of better models that in turn can lead to new insights maybe. And I think this kind of loop is especially relevant for complex biological and ecological systems where we typically have only sparse and noisy observations, and also typically only a partial understanding of the underlying mechanisms. So hopefully this iterative approach can then help us to gradually improve predictions of all kinds of complex Earth system processes and at the same time deepen our scientific understanding. And so with this, I would like to thank you for your attention, and I'm happy to answer any questions that you may have.
Yeah, thank you, Fiona. Thank you so much for your excellent talk. Really very inspiring to see how you can implement these process-based principles in a neural network architecture and achieve population preserving model setup. So while we're waiting to see if there are questions, perhaps I can start the discussion with a question related to that. So if I understand correctly, so you're achieving this population preserving property as far as the migration is concerned, but there is a potential leakage of population of birds through the sync terms. So in other words, you're not accounting for bird deaths and births, for example. There's no underlying population model. Would that be possible, and would that provide additional insights?
Yeah, that's a very good point. I would argue that it's definitely possible. So you could, I mean, you would need to try to separate these processes then. So you would have essentially a source sync term for takeoff and landing, but also for birth and death. And based on the data that we have, I think that's just not possible to separate these. So really what you probably should how you should account this is just that this is included in our current source sync terms. Because if we try to fit our observations in the air and try to attribute all kind of changes that we can't explain by spatial movements, that will also account for birth and death. But I think at the scale of mass migrations, that's really negligible. But again, there's little known about that. So it could be that there's actually quite a contribution of deaths during these migrations because they are quite demanding. Yeah.
Okay. And what about additional ancillary information? I mean, there's all sorts of bird watching going on, bird counts, I guess. Would that be an opportunity for additional validation? So either just as an independent validation or even as additional constraints that guide your process models?
Definitely, yeah. I think that would be a really interesting kind of extension. Validation might be a bit difficult because you have all kinds of observation biases. So you have these citizen science databases of eBird, for example, but that's really more focused on what's happening on the ground, which we don't observe. So to really use it as validation might be difficult, but it might be a really valuable additional information to really constrain our predictions of source sync terms, for example, or really start modeling also the bird populations on the ground to better constrain our takeoffs as well. And another opportunity, I think, is to start modeling this different species as well. So with eBird, for example, you have different data sets for different species, and they might take very different flyways, for example, or the timing of migrations might be very different. So if we integrate that into our model, that I think would also provide a lot of additional information.
Okay. So in the last part of your talk, you also contrasted the AI-based approach against the numerical, physics-based simulation approach, which of course can also be applied in a population and bird migration context. Now there's another type of models that I think they're some conceptual and mathematical link, the cellular automata models. I don't know if you're familiar with them. I believe they're also used in species, population and distribution migration modeling in ecology, which is also a discretization, I guess, closer to those numerical models, often implementing differential equations. And they're used usually as forward models, I would say, but they're hard to calibrate because they have many parameters. So do you think there's also a path for translating such cellular automata models or agent-based models into a neural network architecture, and then leveraging that architecture to better parameterize those models better than, as far as I know, it's been possible in traditional cellular automata or agent-based modeling frameworks?
Yeah, so I do know that there are quite a lot of agent-based or individual-based models trying to model different bird migration strategies, different this decision making in response to environmental conditions. But so far, these are really mostly used to test hypotheses, to evaluate what the effect would be of different kind of strategies on the overall survival, also in very synthetic scenarios. And as you mentioned, these models are really hard to calibrate to real data. So I think that's really the main challenge. And I do think there is still a lot of ongoing work to make this easier, also using some kind of machine learning approaches. So I think eventually there will be a way to maybe merge these two approaches. What I could imagine is that you could encode some parts of these hypotheses into a more population model that is more process guided and with deep learning components, by, for example, further splitting these parts and have kind of a component that really models the response to wind, because there we have a lot of kind of relatively simple, but we do have theoretical models that try to explain how birds move and respond to different wind conditions, so that you could try to encode also into a hybrid modeling approach.
I mean, I guess the cellular automata models are also more likely at the cell level, at aggregated model. But yeah, good point that the agent-based models, that individual-based models, that come with additional challenges, but also opportunities, because then if you have individual-specific and species-specific, maybe objective functions, you can build preferences. I'm not a bird expert, but I assume, habitat preferences, food preferences, obstacles into that. But I assume that some of that is also in your model through, you didn't talk much about those parameters, right? But would that also involve possible obstacles in the path? Do they exist? Like if habitat along the way is modified, there's a new construction site or a mine, some large intervention taking place. How would that or flooded areas, is that reflected by your model?
Um, to a certain extent. I mean, more these dynamical phenomenon like flooding or temporary construction work, not really, but you do have these barrier effects from, for example, large mountain ranges that they try to avoid or have to really carefully navigate through, or large water bodies. So the Mediterranean, for example, you really have these very few migration routes that do essentially island hopping or try to avoid crossing these large water bodies. And we did try to include that to some extent by having essentially a spatial encoding that takes into account some of the geographical features, like, for example, elevation or land cover types. But that's all very implicit right
So
now.
it's static and
Yeah.
it's implicit, but you would perhaps, because you're heavily based on the observational data, you might observe somewhere an anomaly and then encounter, oh, this is because of that particular local disturbance.
Yeah, exactly. But
Okay.
you could definitely try to encode that kind of knowledge more explicitly,
Yeah.
I think.
Mhm, mhm.
Yeah.
For your next PhD.
Yeah.
So I don't see questions coming in the chat, so there's still the opportunity to ask questions there. And then otherwise, do I have any other comments or questions? Yeah, you mentioned equifinality, so you're confident that that was under control at the end with your process-guided constraints. Yeah. Mhm.
Yeah, in the first iteration of this model, we actually didn't account for that. So there we tried to directly parameterize essentially the fraction of birds moving from one cell to the other, still accounting for local mass conservation, but not directly using this finite volume method, numerical flux computation. That still worked to some extent, but you do have scenarios where it just too much variability is attributed to the local sourcing term. And that kind of led to this follow-up work, then trying to fix that issue.
All right. So I guess since there's no additional questions coming in, then we can probably thank you again for your contribution. It was, I think, yeah, very inspiring approach that can certainly motivate similar modeling in other fields in ecology and beyond. And so thank you so much for your presentation and the discussion. And with that, I will give back to AI for Good and yeah, look forward to our next seminar talk. Goodbye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.